Hi guys, I just want to go over the small demo I did in class. So this is you all know what it is. It's a magnet. It has two poles, a north here and the south. Interestingly, so it's called a dipole, magnetic dipole, and there is no magnetic monopole. So it means if I break this, it will be easy. You just drop it. It's going to be broken in two parts. I still have a north and a south. And if you break it again, you have a south and a north. So you can have an electric monopole. You have an electrons on by itself, all by itself. You can have a proton all by itself, but you cannot have a south or north all by itself. If you do find one, then you can get Nobel Prize, right? So magnetic field, you don't see it here, but it's going to go out of the north, loop around back into the south. So I will show you that in my slide, out of the north and then back into the south. So it's looping around. So it means that magnetic field always loop around, whereas an electrostatic electric field can diverge if it's a positive charge or converge if it's a negative charge. So of course, like an electric field, the magnetic field will interact with another magnetic field. So you see north and north will repel each other, south and north will attract each other. So these are action at a distance, and what you see here, or what you don't see, are the two magnetic fields here repelling each other, interacting with each other. So you have different kinds of magnet, of course. So in that case, this is called a bar magnet, and everything happened like we have in the earth. That's what we have in the earth, right? Everything happens like we have a bar magnet. It's not a bar magnet, but it will behave like a bar magnet. Talking about the earth, this is a compass. So a compass is a magnet. That will be the south here, and that's the north. So you see the south is attracted to the north pole, and the north pole here is attracted to the south pole. So if this is north seeking pole, geographic pole, that means that the geographic pole, you have a magnetic south for the earth, right? Because north is attracted to south. So this is a magnet as well that can rotate easily. You have different kind of magnets. So for example, here I have two round magnets here. I don't know if you can see. This is north and this is south. And if I try to push them together, they won't, their magnetic field will interact with each other, right? So they're gonna repel each other. So what's happening is that all the potential energy is stored inside the magnetic field. And of course, if I let go, they're gonna push against each other. I can make a coil gun, right? You have another kind, magnetic fields. So all those round magnets here like this, north is on one side, south is on the other side. And I can use a compass. I see this is north here. And of course, that's going to be south on the other side. You have also what's called the horseshoe magnet. And so with a horseshoe magnet, you have the magnetic field inside that gap here, so between the North Pole and the South Pole, which is uniform. So it means the magnetic field, the vectors have the same magnitude and the same direction. So inside the gap, the magnetic field goes from north to south, right? And you can see that that's going to be the south here, and that's going to be the north. Although this magnet has been demagnetized a bit That's why you have to use those things here to try to keep the magnetism, okay? Because they are not real permanent magnet; they are cheap magnet. Right. So I wanted to show you also the experiment by oersted that we talked in class. I just have moved away the magnet. So here I have a circuit. You see, I have a 9-volt battery and I have a switch. And this is my compass here. No, you can not see the compass here. This is the compass here. And I'm going to try to... So the source of magnetism is electricity or moving charges, right? So each time a charge is moving, it's going to produce a magnetic field. Even inside a small magnet, permanent magnet, like I showed you before, it's because those electrons are spinning and they behave like small currents, loops of current, and they make that magnetic field. So you see here the needle stop moving. I'm going to close the switch here, and you should see the needle moving now perpendicular to the wire. So what does that mean? It means two things. It means that electricity generates a magnetic field, and that the magnetic field is going to loop around the wire, right? It's going to circle out. So try not to move the needle. I don't know if you can see. And close it very quickly. Boom. So see, the needle has moved and try to position itself perpendicular. It's not quite perpendicular. That's because my battery is out of juice. So what I can do, I can take another battery that should be working here. And we can start over. So here, this is perpendicular, and I'm going to close it. And now you see that this was parallel, and now you see how it's going to be perpendicular, right? Because you have a lot of more juice here. So now, if I reopen the switch, the needle will be parallel, right? So I cannot do that too much because it's a short, but you see here it's parallel, and if I close the switch, it's going to try to be perpendicular, more or less. I'm also losing a lot of juice from here. Okay. So what's happening here is that the magnetic field, when electricity is flowing, it's going to loop around the wire. It's going to be strong close to the wire. So you're going to make those lines close to each other. And then as you move away from the wire, you still have magnetic field, but it's getting weaker and weaker. It's an inverse relationship. Okay? So then I show that how an electromagnet works and how you can build one if you want extra credit, if you want that. You see that I can make a circuit here. So what's happening here, nothing happens. It's not a magnet. It doesn't attract here, right? Because electricity is not flowing inside. So what you have here, I have core. It's called a core. So it's an iron core. And you have a wire that has been isolated. It has like a small varnish on top of it, right? And wrap around. And that's called an electromagnet, and that's going to behave like a bar magnet, okay? So I'm going to have electricity flowing For that, when I close the switch, so here I have my electromagnet. I didn't close the switch. I have paper clip, and I'm going to close the switch here. And now you can see that I'm going to have a magnet. I don't know if you can see it. It's hard to be here, but you see I have a magnet. And I can show you that I have a magnet using my compass. You see that? That's going to be the north, and that's going to be the south. So I have made like an electromagnet. That's because electricity flowing make a magnetic field looping through the core here. So it means that when electricity goes around this way, the magnetic north will be in this direction. That's going to be the south. Okay, so that's the north. That's because electricity is flowing. I use my right hand rule. That's going to be the north. That's going to be the south. And it's getting very hot. Interestingly, even when I open the switch, some of the domain inside the iron core stay magnetized. So it's going to still be like a magnet, even though the switch is open, it still behaves like a magnet. Okay, it keeps its magnetism. So it's like I have made my own permanent magnet, still behaving like a magnet. So it's not great if you want to use that to lift a junk car like wreck. Instead, use this here. It's like a solenoid. It still have core inside. That's just wires that have been isolated. And I can connect that here. So I have my electromagnet. I didn't close the switch yet. So I close the switch. And you see that I can put up. I have a very strong magnet here. Not very strong, but still an electromagnet. I don't know if you can see. I have picked up some paper clip. And what I want to show you is that as soon as I open the switch, boom, I lose the magnetism. So you can use an electromagnet to pick up pieces of iron or car that are not used anymore. You pick them up, you move them, you open the switch, so you drop them. They have a lot of application for this. So for example, here I have like a bell. Ringing bell, and you see here I have a small electromagnet. And if you can see my tiny electromagnet, and if I close the switch here, boom, you see I can pick up paper clip, and then I can have my electromagnet here. And if I close the switch, it rings the bell. So that's how it works, right? It's a very simple demo, but maybe it inspires you for if you want to make your own demo, make videos, especially if you like to build an electromagnet. You see, what you need is the screwdriver, so that's easy to get. You need a wire here, which is small in diameter, but that has been varnished here. So it's isolated here. It's called an enamel here on top of it. And here you have to send it out, of course, to make the connection. And you have yourself an electromagnet.